Welcome to my ENC poster. Today I'm going to tell you about this spectrum. This is the oxygen spectrum of gadolinium-doped ceria, oxygen-enriched, recorded under MAS DNP conditions. So this scale is in hertz, and this line is only 2 millihertz wide, which is an exceptional resolution in the solid state. So how do we get this? It all started when I was trying to tune the probe, and the wobble curve started doing this. So this was very confusing, but this looked like to me like the sample was shooting RF back at me. So I thought, okay, what happens if I go quiet with no pulses? So I wrote a very complicated pulse sequence, turned on the receiver, and this is what you see. Bursts of transverse magnetization, which decay and then reach a steady state. If you zoom in on one of these bursts, you see that it's actually processing, and it processes at the Larmor frequency. So if you Fourier transform, you get a peak at the chemical shift, in this case 875 ppm, but it's much sharper than the conventional FID because this signal goes on for longer. So what's going on here? So this is known as the Raser Effect, and you might imagine that this is similar to lasers. And lasers, you require large population inversion and optical feedback, whereas in NMR, the large negative polarization we can achieve, for instance, with solid effect DNP, and in our case, we get a peak enhancement greater than 500. And the feedback occurs via radiation damping. Radiation damping is an effect that rotates large magnetizations towards plus Z due to coupling with the coil. If you start with transverse magnetization, this is an additional source of decay. Whereas if you start with negative magnetization, your radiation damping rotates into the transverse plane, which spontaneously generates transverse magnetization. The rate of radiation damping is given by tau RD, and importantly is proportional to the size of your magnetization or polarization P. The Raser effect occurs when the rate of radiation damping exceeds the rate of decay of transverse magnetization, i.e. tau RD is less than T2 star. In the solid state, we can increase T2 star using MAS and activate the Raser. So when we're static, there's no Raser effect, and as soon as we spin up, we see these bursts of transverse magnetization, and we can reversely switch the Raser effect by varying the MAS speed. Once we're processing, this goes on indefinitely, and so in principle, we could get arbitrarily sharp lines in our spectrum. In fact, we're limited by field stability, and in this case, the field happened to be most stable during this region, and if we Fourier transform, then we get this spectrum I showed at the beginning with a 2 millihertz line width. We can also apply filters to remove truncation wheels. With that, I'd like to thank Snedis, Linden, and Claire. And if you'd like to find out more, for instance, why we get those bursts of magnetization in the Raser effect, what makes gadolinium ceria so special that allows this to happen, or any other questions, you can email me, you can check out our recent paper, or come to my breakout room. I'm in post session 1. Thank you for listening.